was able to access to his group?
Yeah.
Okay. Let me now share with you something. Since I would say 90% of you got the board, or still?
I'm still waiting for it to get here.
Okay, so expecting to getting it when? Oh, so it's like roughly now. Okay, that's good. Let me share what I'm gonna talk about today, and then we can move forward.
Professor, I don't think I got an email from you.
Huh?
I don't think I got any emails from you.
About what? About the GitHub?
Yes.
That's something we're gonna share now, and we can see who is who, right?
Okay.
So,
Perfect.
everybody can see my screen?
Correct.
Okay, so good. Here's the organizational that I made. And so group A, I'm gonna take it group by group so we can be done. Group A, right? Here is the setting, right? Here is the team collaborators. Joseph, you haven't accepted yet.
Okay, I see it now.
Right? I can send you a new one here. Is this your name or I made a mistake?
No, that's me.
Okay, so I already see pending invitation. Okay, but Sami Elias already got it. Now let's go in a group what? B. Group B, setting, team. Both of them are already in. Group C. Setting, team. Both of them are in. Group D. Setting. Both of them not accepted yet. So is Mario?
Yeah, I just tried accepting it, but it says the 404.
You have to log in.
You have to log in. So, and also, for the other one,
Professor, I'm logged in. I'm still getting a 404 as well.
It's giving you it's not correct?
Yeah, me too.
Let me see. Okay, we do it again. Okay. So now Mario, right? It is Mario 4404, right? Is this the one, right?
Yeah.
I already added you there. Is this you, Joe?
Yes, that's me. Rogelio?
Yes.
Yeah, I'm getting a 404 too.
No, you have to accept the invitation. 404 if you just click on the link. You understand? There is invitation. Everybody, you got the invitation, right? You understand what I'm saying? Look at the email you are using for the GitHub. You will find an email sent to you say that accept this. Accept it, then you will not get 404. Can you do, please?
I haven't received it yet.
Check your what's called junk or whatever, different folder in the inbox. Exactly, correct. Sure, when you're right. So you have to accept first the email, and after that you will click the link, then it will be open. Okay? So let's wait for Mario, so I can move forward with the rest.
Yeah, I don't see anything on my email.
Which email did you use for this GitHub?
Should be CPP, but...
Are you sure?
Well, that's how I got the first one, the first invitation.
Yeah, so there's two emails that got sent, so make sure it's the recent one. I got it working, but there's two invites, so that's why one wasn't working for me.
Mm.
All right, I just got it working.
Should I remove it and add you again or what?
Yeah, my email is linked. That might work.
Remove, cancel Mario, cancel. Okay, I cancel both of you, right? Then I go in Canvas. Give me again your, add in the chat your username for the GitHub.
It's Mario 4404.
Write it in the chat. This one, right? Admin.
Yes.
Yeah, you got anything?
Yeah, I just came in.
Okay, good. Now, the other member, what's his name?
Yes.
Can you write it in the chat? Here, check your email. Maybe you accepted already. You receive it?
Yeah, I got it.
Okay, let's see. If you accept it, automatically will be on. Okay,
There.
you're in. Now we're gonna move in the group E. Both of them accepted. Group F. You haven't accepted yet.
Professor,
Hmm.
yeah, I didn't get the invitation as well.
Okay, can you write your thing again?
My username?
Username for GitHub, yes.
Yes.
Place it in the chat.
Okay.
Here, right? Admin. Did you receive it?
I'm refreshing my... No.
Did you receive it or not?
No, no. I don't know why.
Are you sure you are using the right email? Because maybe you created this with another email address you have. Right?
You can get back to me later, if that's okay. Let me see.
No, that's fine. I would like to be sure everybody's in. We're not gonna take that much time today. It's just like, we're gonna talk about something and then the task and then you guys start working. Go ahead.
Yeah, you're right. I used another email. I just checked. Yeah.
Yeah. You found it, right?
Yeah, it's not on my CPP email. That's why. Yeah, I received the invitation.
How is it now? You got it?
Yes. Let me log. Okay, I guess I'm in.
You're in now, right?
I guess I accepted the invitation. I don't know if you can see it.
You accepted?
Yes.
1 second.
Oh.
No, you haven't.
So,
Anyway, we'll move to the other group
okay.
while you're
Okay.
fixing this, okay? What about those two? Cancel, okay. Okay, remove this. Oh, you accepted? Okay, we'll check it now. Anyway. Okay. So Noah, you accepted? Okay, both of you accepted. Let's revisit again D. Okay, D accepted. And you guys were F, right? Yes, you accepted, you're right. And G, you already accepted.
Yeah, thank you.
You're welcome. So now we're gonna go H. Good, both of you accept. H, I. Both of you accepted. One of you accepted. What about the other one?
My username, you're missing 2 I's at the end.
Let's do it again. Let's do it
I
again.
already put it on the chat.
What about now?
Check. Got it. Thank you.
So, perfect. Yeah. Okay. Both of you accept. Okay. Perfect. 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 Okay, perfect. So now, we have the 15 groups and, all of you guys are in, right? Okay, now I'm gonna share with you some information and maybe report from other teams like ECE3300 lab, food 21. For instance, just go Google, right? Do you guys see what you already have done here? They have what? They have lab name, whatever, right? Let me find you a better group. Look at the lab, right? They make what subfolders, right? And then they wrote what in the README about themselves, like group 1, they work in the lab 1, they did whatever, lab 2, whatever, lab 3, whatever, and so on. Then if you open the lab 1, you will find what code, and you will post your code, and then you will put what documents, and the documents will be your slides, presentation, the report, and the report in a PDF, and a video for the demo. Does it make sense to everybody? Any questions so far?
How did you get to that?
Huh?
How did you get to that?
What do you mean?
To those files.
How do you already load the files, you mean?
Yeah, are we supposed to have those files already?
You will load them.
Oh, okay.
That's really easy peasy, it's not really hard. I already posted on the Canvas, right? Something about GitHub, right? Did you guys have a chance to watch it?
Yes. Yeah.
Exactly. So better for you to watch it. Anyway, so then lab 2, you open code, you post your code, then what? Documents, presentation, report, and demo. And we can open one of the reports, just like see what they have. So the reports, they will list here, let's say lab 2, professor, whatever, group, you put your name and Bronc ID, for instance, right? Then you put the contribution, who did what? Then, they start describing their code. Maybe this is not really better example, but, I will find you like a report, you can look into it and I will send it as a sample, okay? But at least you know what you're gonna do with GitHub, right? Everything you're gonna create a folder under the group that will have the lab name of the folder. Inside there is 2 subfolders. One is called code and one is called documents. Code, you place all of your codes. Documents, you're gonna put the presentation, the report, and the demo. Make sense?
Professor?
Yes.
With the code, would you want them in as they have it in a text file or?
Yeah,
okay.
the code, like, the whole entire project. Do you remember? I don't know. Are you part of my course?
Yeah.
Yeah, if you're part of my course, right? I shared already my code there, right?
Right.
The whole entire folder, visit.
Okay.
Okay. Sounds good to everybody?
Sounds good.
So, who is not taking this course with me? The ECE3300. Is anybody from the attendance that not taking the course with me?
Yeah, I'm taking it in a different section.
Okay, who else?
By that, do you mean with the different professor?
Yeah.
Yeah, me also.
Okay, who else? Joseph?
Yeah, I'm taking it with you.
Okay, for the people who are not taking it with me, Irving and the other and Joe, right? Who else?
Me also, Professor.
Okay, because do you guys want me also to put a copy of my course material in the lab? If you want.
That would be great. Okay,
I'll do that. Okay, anyway, let me share my tablet so I can draw to you what is exactly what we're gonna do for this specific lab. So let me go zoom. Sorry.
Bless you.
Thank you. Okay, everybody can see my screen?
Yes.
Okay, so now back, git up. You're recommended to do what? The folder name of the lab assignment, like, lab 1 underscore date. And the date is basically what? The date of issue or the due date. Okay. Under this, there will be what? Two subfolder. One is what? For code. Another one for what? Documents. Under the documents, you will have what? Presentation. Slides. Demo. Like I recorded. Video. And the report. And the report will be in what? An award and PDF. So far, so good? Okay. Now, since, we are talking about the lab 1. So that's basically what we need to do. Lab 1. Everybody remember the combinational circuit. Do you guys remember combinational circuits from the 2300?
Yeah.
Okay. Do you guys remember decoder?
Yes.
Okay. There are two different types of decoder, right? There is a decoder active low, and there is a decoder active what? High. So far, so good? The decoder is active low, active what? High. Now, the decoder can come with enable signal, or it can be decoder without enable signal. Do you guys remember that or not?
Yeah.
Then, everybody with me know what is for generate, right? For the Irving and the rest. Do you guys use for loop?
Yeah.
No,
That's what you showed on
people
the.
are not taking with me the course. Huh?
For loop?
Yes. Have you used the for loop?
Yeah.
The for loop in Verilog, did you use it, right?
No, we haven't used the for loop in Verilog yet.
Okay, so you might actually watch the video I'm gonna share, okay? But there is something it's called for generate, and there's something it's called gen var. Okay, those things that we're gonna use. Okay, I will make example in front of you. So let me share my. Let me open Vivado while we're talking, because my Vivado takes some time. I have to click multiple. Okay, so for the decoder, somebody remind me how the decoder look like. right? Decoder, right? And the decoder, it has a bunch of inputs, and those will be having outputs here, right?
Right.
And the relation between the input and output is what?
2 to 4.
Yeah, exactly. So if you have here, I, they're gonna be 2 power I, right?
Right.
So example, you already have 2, 4, right? So here, 2-bit, the output would be 1, 2, 3, 4, right? 2, 4. There is also what? 3, 8, right? Sounds good? And there is what? 4, 16, 5, 32, and so on. So far, so good? Okay. Let's see what is the circuit inside the decoder, right? So the first part of the lab, let's have example 2, 4, right? So 2, 4 decoder, 2, 4 decoder, right? That, right? Let's say this is 0, S1, and here's what? O0, O1, O2, O3, right?
Right.
How can we build a circuit? We have to use what? Truth table. Do you agree?
Yep.
Here's the truth table. S1 is 0, O3, O2, O1, O0. Then how many states this table will be covering? Huh.
4 states.
4 states, right? 1, 2, 3, 4. Somebody tell me why it's 4 states.
Because there are 2 inputs.
Correct, you're right. So, 2 power number of inputs, you're gonna define number of states, right? Sure. So here we're gonna be what? 0, 1, 0, 1, 0, 0, 1, 1. Because this 2 power 0, 2 power 1, right? So 2 power 0 is 1, that means they flip every time. 2 power 1 is 2, that means every 2 and you flip. Right? Okay. How the decoder work? So basically, one of the output will be active, the rest will not be active. Do you agree? So here's 0. The second, if you remember, that was M0, M1, M2, M3, and those are called what? Mean terms. That was from the 2300, if you guys remember, right? So you have here 0, 1, and gonna be here 1, 0, 0, 0. There we're gonna be 1, 0, 0, 0. They're gonna be 1 and 1, 2, 3. Sounds good?
Yep. Yes.
Okay. Since we started introduction with Verilog, so we are using gate level, right? Gate level implementation. You guys agree? So in that case, we have 4 outputs coming from 2 inputs, right? So for instance, this one, if you write the regular expression of it, algebra basically, as a function of S1 and S0 is equal to S1 complement ended with S0 complement. You guys agree?
Yeah.
Yes. Then O1, S1, S0 is basically what? It's S1 complement S0. Then O2 as a function of S0 and S1, it's gonna be the flips. It's gonna be S1, S0 complement. Then the last output S1, S0 is gonna be what? S1, S0. So far so good?
Yes.
Those are what the Boolean equations describing the relation between input and outputs in the decoder, right? Implementation. If you would like to implement this, how gonna work? So you already have here what? S0 and you have here S1, right? Let's start using colors. So here, right? And we can write here what S0 complement, S1 complement, right? And then we start making the connections. So here is the color. So first of all, I'm gonna take this and I take this, and that will be ended together. They're gonna bring O0, right? Then the second possibility is gonna be what? Take this with S1. O1. Then the reverse, right? Oh, stick. Right? Everybody agree?
Yeah.
So if you would like to write a code for this, what you're gonna do? Somebody tell me, what you're gonna do to write a code for this? You're gonna create a file, and this file you can call it what? Decoder 2x4.v, right? Then inside the file, you're gonna write what? Module space deco 2 times 4, right? Then you go here and module as a one word, right? Then you know you're gonna open here what? A parentheses, right? What is this parentheses? It's gonna be what? Input 10 S, right? And then you know you're gonna write here output 3 to 0, and they're gonna be P. Let's make it P, right? You guys agree?
Yeah.
You know what is those? What is those, right? This is S0, S1, and this is the 4 outputs, right? Then you know to have enough space, you're gonna write here what? You're gonna say that you know P P0, right? P0, and that will be S, right? The NOT gate of S1, the NOT gate of the S0, whatever, right? And you continue. That makes sense to everybody?
Yeah.
Of course, you don't need to make it exactly like I'm saying. You know, you can actually clear this and you can be more tricky, right? I'll show you how. You can actually create a wire. It's called S underscore negation. S0 underscore negation, comma, S1 underscore negation, and you close, right? And then you go here and you say what? Not N, I'm sorry. Not S0 underscore negation, comma, S0. Not S1 underscore negation, comma, S1. Then you go here and you start building your full end. and you open. Here we're gonna be what? B0, comma, B1, comma, B2, comma, B3, comma, right? Then you know what will be the click here. With 3, everything is normal. So gonna be what? S1 with S0. With the other one with 2, you already have S1 with the S0 underscore negation. With the 1, the verse, right? So gonna be what? S1 underscore negation, comma, S0. And then there we're gonna be what? S1 underscore neg, S0 underscore neg, and you close. And then you write here what? End module. That makes sense based on what we learned.
Yes.
Yeah, Professor, one question.
Sure.
The way you showed it before, we could also just do S not or not and then S0. We want to negate S0.
I mean, you can try it, that's true.
Okay.
I mean, there is multiple way, but this is git level. That's literally git level. You can use data flow, right? So you can make like the delta like this.
Right. Okay.
Right. This is when you use it. That's gonna be data flow. If I say that, let's say build the git level, right? So you build it like this git level. There's a bunch of gates, right? So this is very simple, right? Do you guys agree?
Yeah.
Now to build a test bench for the people who didn't attend with me, did you guys learn how the test bench look like?
No,
we
not
haven't got
really.
Easy. That's not really hard. I'm gonna show it to you now. Anyway, back to the importance. Now, what about if I would like to build a bigger size decoder from a small size decoder? What should I do? So for instance, my cell, the smallest is 2.4, right? If I would like to build it with, if I want to build 3.8, what should I do? Somebody tell me.
Would you create 2 instances of the 2x4 module?
That's very good. That's very good. But don't forget, right? You have to be tricky with them, right? It's not like a straightforward, have 2 instances and, you know, and that's it, right? You have to do something in the middle, right? Also, there is another question. What about if I would like to build from this 416? So let's try to, first of all, define 2.4, right? 0.0, 0.1, 0.2, 0.3 with what? Enable. Right? Make sense? So if I look into the enable, so that means I have enable, S1 is 0, and then I have the 0.3, 0.2, 0.1, 0.0, right? How many states this table would be covering?
8.
Huh?
5? Is it 5?
It's 8. It is 8 or 5, you're right.
I think it's 5, right? Because the enable.
Correct.
Yeah, it's 5, I think.
It is 8, should be 8, but you know, I will show you some. It is 8, but efficiently it's like 5. I will show you how. So 0, 1, 0, 1, 0, 1, 0, 1, 2, 3, 4, 1, 2, 3, 4, right? These are the active one, especially if the enable is what? Active high, right? So as of some of you already said, so those 4, there is no signal, right? So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1.
Sometimes.
Right? The active is gonna be here, right?
Can I do something?
Correct?
Then
That makes sense?
Correct.
your computer can charge my phone while you're.
So actually you can write the table like this. 1, 2, 3, 4, 5, right? Enable S1 is 0, 0, 0, 1, 0, 1, 0, 0, 0. No, sorry. If it's 0, XX, and then 0, 0, 1, 0, 0, 1, 1, 1, right? Like that, right? Then you know 03, 02, 01, 0. Here, I have no idea. Or you can make it just zeros. There you can make what? 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 2, 3, 1. Correct? You guys agree?
Yeah.
Yes.
Okay. So this is correct. This is correct. Sounds good? But what is the implication in the implementation? Right? So if I have this guy enabled here, right? Added. In that case, what I'm gonna do? It will jump here, right? Jump here, jump here, jump here, right? Like an extra port enabled to the end, right? It's correct?
Right.
Yes.
Which is like an extra end. So, you know, the normal end is like this, right? The 3 input end is equal to what? 1, 1 out and like that, right? You guys remember this?
Yes.
Yeah.
Yep.
Perfect. So basically we need something like that here, right? Okay. So now at least we understood what is the enable. So let's construct bigger decoder, right? So bigger decoder, how gonna look like? So we're gonna have here, as you guys said, you know, 2, 1, 2. Here I have 1, 2, 3, 4. 1, 2, 3, 4, right? Then I have here what? Enable. Then I have here enable, right? And here gonna be what? Since it's 3, 8, right? It's a 3, 8. Do you agree? So in that case, it's gonna be what? 0, 0, 0, 1, 0, 2, 0, 3. Another one is gonna be 0, what? 4, 0, 5, 0, 6, 0, 7, right? And that's actually 2, 4. They're gonna be 2, 4. Now, to make this happen, one of them should work at a time. Do you guys agree?
Yeah.
Yep.
Perfect. So what we are saying here is a negation of the third one, while this guy connected like this, and this guy connected like that, and that are gonna be S0 and S1, right? And this is what S2, and that will be connected like that, right?
Right.
Let's try it. When this is equal 0, that 0 will go here to be 1. So this area will produce the first 4 from the combination of S0 and S1. While when this turn to be 1, this will be disactivated, and the 1 will be on as this. Then this S0 and S1 here will be jumping into the O4 to O7. Correct?
Correct.
Okay. What about if I would like to move into instead of 3.8 to be what? 4.16. So it's gonna look like. So 4.16 is gonna be here what? 2.4, right? 2.4. 2.4. 2.4, right? Sounds good?
Yep.
Correct? Then we'll have this guy come out like this, which is gonna be another level of what? A decoder with what? S2, S3, right? Now your job, I want you to build a generic decoding system, a generic decoding system using 4 generate. Using 4 generate. I know some of you don't know what is 4 generate, right? So that's why I'm gonna show you now example I have made about 4 generate, and from there you can understand what's going on. So what is the task? The task for this week. 1, right? Using gate level to implement what? 2x4 decoder. The code I wrote already, right? You just need to what? Implement it, correct? Then task number 2, which is 2, right? Make your circuit flexible to run different decoder sizes. Using what? Parameter plus 4 generate. Then 3 generate test bench, right? And this test bench what? Testing corner cases. What corner case? What does it mean, corner case? I'm gonna show you test bench how it works. But what does corner case mean? Yeah, 1 second, please.
Oh, probably for the next month.
Oh, okay.
Or whatever's in there.
Okay, but I didn't get the switch for the network, right?
Not yet.
Not yet, yes.
Yeah, there's a bunch of stuff coming, so it'll come in a bunch of different boxes.
Thanks so much. By the way, I'm a little bit confused. You told me that the surge it was $85, then you checked again, it was $80.
I rechecked an email that I had with you. It was $80.76.
That's fine, whatever. Yes. Thanks so much. Have a good one. Okay, sorry guys. Anyway, testing corner cases. What corner? What is the definition of corner cases, guys? Is anybody aware of what corner case mean?
Are you talking about like the minimum and maximum values it can handle?
No, corner case for us as a hardware designers, yes, it's edge cases. It's basically the cases that it might look perfectly on the circuit, but it will not work. Example, if I have a counter, everybody know the counter, right? So the counter is counting 0, 1, 2, 3, 4, 5, 6, 7, and then it will go back to 0, right? So corner cases to check if 7 gonna go back to 0. That's a corner case. Because it might not go to 0. Right? So corner case here, right? Corner case here, right? I go, I keep jumping 0. I have 1 here. I have 1 here. I have 1 here. I have 1 here. 1 here. 1 here. When I have 1 here, if I flip again S0 and S1 to 0, 0, 0, is it gonna go back here? Or luckily it's gonna move something in the middle. Then we'll figure out there's an error. That's a corner case. So 99% of the people who work in as a hardware design engineer, let me tell you a story. So designers, right? I used to be a designer. I used to work as senior design engineer. So, designer, 30% of their task to design, 70% for their task is to what? Verify the design. Can you imagine that? So you take 30% of your time to build something and 70% to check if the thing is work or not. Does it make sense?
Yep.
Yeah.
So I want you to use your imagination. In the decoder, what possible issue can happen? And from there you can assign tests. Make sense? That's why here what? Generate test bench testing corner cases. Okay? Then number four, run on board a simple example of decoder using switches plus LED. Somebody will tell me why, right? Switches will be what? The input for the input for what? For the decoder, right? LEDs will be really good for what? Showing something blinking. Huh? Joe, what do you say? Joe, do you have a question? Hello? I cannot hear you.
No.
Okay. So now you understand what I'm saying, right? So let's summarize so we'll not be confused, right? So first of all, our task of this week, what? We're gonna build git level of the 2.4, right? And we already have the code here, right? We just modify and see how it's gonna look like, right? Second is what? To build a circuit, it's generic. So that means using what? Parameters and a for generate. And I will show you now example for those people even doesn't know what's going on. And even for the people who work with me to just like, refresh their knowledge, right? You build it, perfectly fine. Go in a test bench and test the corner cases to see that your design is perfectly fine. Your design is perfectly fine. Connect some switches and LEDs to a simple design. Doesn't need to be huge because, end of the day, your board has 16 LED and 16 switches, right? So be careful from the limitation. You cannot jump up to 32 LED for instance. Of course, there's a trick to do it, but not now. The next lab. Okay, sounds good. Any questions so far regarding what is the task and what we need before I will show you example about how to run on the test bench and the for loop and stuff like that? Hello.
No questions.
No question.
Everything is like crystal clear. Everything is clear.
Yeah.
Good. Now we're gonna close this. And we're gonna go to what? To my Vivado. I'm gonna share with you again the code that I wrote last time with you guys for those people attend with me. So all of you guys know how to use Vivado, right? Joe, for the people who is not attending with you, with me, you know how to open Vivado, right?
Yes.
Yes.
So, I generate something here and I call it week 2, right? I'm opening it. Take some time.
If you don't have the file, we put a create project, correct?
Yeah. As I told you, I'm gonna include my video for the last lecture for my course. You can watch it also. Okay. It's already in the material for the course, right? Anyway, everybody can see my computer, right?
Yeah.
Right.
So here I built example with my course members, right? What was about full adder. Okay. So here in the full adder, normally my way of working, I write some information about myself here in the comments. So every time I do some work, people will recognize who did what, right? So try to fill this as much as you can. Is it clear? It is a way that, you know, for good readability. Then here, everybody know what is full adder. Do you guys know full adder, right? Full adder, that means it has 3 inputs, the carry in, the 2 operands, and the output is the sum and the carry out. Do you guys agree?
Yeah.
Yes.
So here is 3 inputs and 2 outputs. The way I name the signals, the way I name the ports, if you noticed, since it's a full adder, so I start everything with what? FA underscore carry in, FA underscore port A, FA underscore port B, FA underscore port underscore sum out, FA underscore port underscore carry out. This is my style. Okay. Then whatever wires or registers or whatever I would like to use, but since, you know, we are in the lab 0, so basically, you know, we cared up much about to know there is wires, right? And this is a good level. So intermediate wires for the XORing, whatever, like when we did with NOT gate, if you remember, right? Then I define those wires. Then I know in the full adder, it's 3 of them gonna be XORed, right? So what I did, I XORed, concatenated with another XOR. All of this together is doing the carry out, sum out, the sum, right? Then that part is responsible for generating or propagating the carry what? The carry out. Any questions so far?
No questions.
All good.
Perfect. Then I went to generating or creating. So for those people who didn't work with test bench, look, I said add source, and then, you know, you create or add simulation source. Okay. I created a test bench for this single bit full adder here. Everybody can see it, right? So how we create a test bench for the full adder? First of all, there is no longer input and output port for the test bench. Test bench is just a test bench. End of the day is .v. Okay. Then I treat it exactly like a breadboard. In a breadboard, right? You bring your IC, right? You open your what? Your manual, right? And you start saying, oh, this pin and this pin as this pin are input. This pin and this pin and that pin are outputs, right? So my IC, the one I created, is full adder, right? So I did something here, it's called what? Instantiation. So I instantiated. Everybody heard about instantiation?
Yeah.
Irving, you know instantiation?
Like classes?
You got it, right?
Sure.
Okay. So we instantiate this full adder. But the wires we are connected to the input and outputs, we are defining them here. So any input will be pushed to the instantiated block. We're gonna make it what? REG, which is mean register, because we're gonna fill in some information, 0, 1, whatever, right? Any output for us is what? Wire. And I name it here, see? FACN, but this time it's in that side that is bench. So that's why underscore test bench. This one, FA port A is test bench. FA port B, test bench. Sounds good? Same thing for the carry in and out of the IC. I built this a full adder. So FA port sum out TP, FA port carry out TP. Then while I'm connecting, I connect those guys here. So those two steps is officially putting the FA as a IC on the breadboard and having those wire hanging out of the breadboard, waiting for me to communicate with them with the what source of voltage or current. Sounds good so far?
Yes.
Okay. Now, how I'm gonna inject inputs inside the inputs so I can see the output, right? So I use something is called initial block, which when you write it is initial, begin, and end. And I give it a name and I call it test one. So if you like to name initial block, you put like, double columns and or 4 columns in front, and then you're gonna write whatever you want in front of, okay? The initial block has a feature, which is basically, it's a snapshot of time. What does it mean? That means that, I can fill the inputs here and looking into the outputs in something is called waveform, okay? So here, if I run this without including the others, that will be zeros forever. But I add time here. So this is a time factor. See, this is basically delay to apply different values for the same input ports. Make sense? So I said here, put the CN with 0, and I put it with A and B with a different way to represent input. So for instance, here, is 1 bit binary. Here, 1 bit in decimal, write it 0. Here 0 because, it's gonna be written 0 no matter what. There's a way of representation. Did you guys learn the representation and numbers, right? In Verilog.
Yeah.
Okay. Now, after 10 nanoseconds, because this is the smallest time I can make, right? I said that, apply 1, so put 1 on the port of the CN, put 0 on the port of A, put 0 on the port of B. So far, so good? Then after 10 nanoseconds, it changed. After 10 nanoseconds, it changed. And after that, wait for 1,000 nanoseconds and then close the test case. I don't need anymore.
So that's essentially just going through the truth table.
Exactly, the truth table. Perfect. So basically, that's why, so I can picking up what is my corner case.
Okay.
So far, so good?
Yep.
Now, and I close the module and everything. Now is the time to represent the output. I haven't seen the output, right? There is 2 ways. One, I can make it inside here by inserting something that's called props, but I haven't teach it yet. And actually, it's really higher than, undergraduate level. But I'm gonna give it to you guys, but not now, not this week, too much. Why? Because, I want you guys to be perfect to go for internships, okay? But what I'm gonna show you here is simulation. So we can visualize the output coming from the input we forced it in, okay? So everybody can see my cursor, right? Is it standing on front of what? Around what? Simulation.
Yep.
Is it clear to everybody? But beforehand, my top design, it's actually pointing to n bits FA. But I would like to test what? Single bit FA, right? So I can stop here in any of those and I click right and say what? Sit as a top. So now I have 1 bit full adder as a top. Then I can go into my test bench and which FATP, I click on and I said sit up as a top. So now I'm sure the test bench I'm selecting to be running is running for the 1 bit full adder. Thus, if you already have many other modules defined in the project. Okay, now I see the 3 lines, the 3 points with the green in the top is pointing to the 1 bit full adder. and also pointing for the 1-bit for adder as a RTL. So I will run simulation. There is a list of simulation in front of you here, options. The one we are running, it doesn't involve any synthesis on the chip. So the one we're gonna choose is the run behavioral simulation. I click on it. It's what start taking the process to generate something is called waveform. So far, so good.
Professor, I got 2 questions.
Sure.
On the simulation, do we go through the whole truth table or just certain?
It's up to you. Whatever we're gonna write here in the initial, whatever will be popped out here.
So you, like, for example, for the decoder, you wouldn't go through all
a decoder you can, of course. I mean, that's why I'm saying that it check the corner cases, right? But this is just a 2 example, right?
I see. And then on your sources, when you had like 8 different sources,
yes.
Those are 8 different projects you had, or there were?
No, I will show you. I will show you now. I'll show you. That's something else. Okay. Anyway, because I was running example before to the other group, right? Those are the signals I need. So look, I stopped here with shift and I move the cursor and I select everything. I can just grab it like that. And I say save. Okay. So far, so good. Now I'm gonna go in what? Look at this, restart. And then I will just run. Everybody see what happened here? Irving?
Yeah.
So what is presenting is it's a visual representation for whatever we give it to the system, right? So look, for instance here, right? In a 0 nanosecond, I told the system to consider the carry in and port A and port B zeros, right? And the consequence of that, ports sum out and carry out are equal 0, right? Now, after 10 nanoseconds, I told the system to force the carry in to be equal 1, while the A and B equal 0. Consequence for adder has 1 and 2 zeros, the sum will be 1 and the carry out will be 0. After 10 nanoseconds, I told the system to make carry in equal 0, while A is equal 1 and B is equal 0. Consequence of this, the carry out, the sum will be 1 and still carry out will equal 0. Now, one of the possible corner cases, if all of them equal 1, we are expecting what? Sum will be 1 and carry out will be 1. So in that case, here 1, 1, 1, the sum out went to be 1 and the carry out is equal 1. Another corner case, if 2 of them equal 1, so we need to be sure that sum, it will be 0, but carry out will be 1. Do you agree? I haven't done this part, but we can add it here maybe after this specific part. So you can take a copy here. And we can just go ahead and say that, you know, if this is equal 0, what will happen? Right? And also you need to be sure the values will be changing, right? Because maybe those 2 ports with 0 is doing correct, but maybe when that one go here, it will not be correct. You understand what I'm saying? So in that case, I can just go ahead and say what? Rerun simulation. It say close. It will regenerate. What happened? So in the case here, right? 1 and 1 and 0, it brought me what? 0 in the sum, and the carry out will be 1. Everybody agree? So in that particular case, the chances for this adder is actually correct, is almost 100%. Make sense to everybody?
Yeah.
For those people who doesn't notice bench, does it seems okay to you?
Yeah.
Okay. Don't forget, the lab is recorded, so you will watch this also, right? And I will add also the video of the lecture. Okay. Now, the second part I promised, which is basically the 4 parameterized, right? So everybody know that 1 unit bit full adder, if it gets consecutively connected to each other pipelinely, so we're gonna have n bit full adder, right? For instance, if I would like to have 2 bit full adder, I will have 1 bit full adder, 1 bit full adder, and the carry out of the first one will go to be carry in for the second one. You guys agree? So now you click on the FA n bits, which is basically instantiating 1 bit full adder with parameterized and for generate for flexibility. So how to generate the parameter? So first of all, under the module here, right, we define the parameter as you can see. So you already have here the hash door, and then you open the parentheses, you write a parameter, then you define a parameter, which is for instance data width. Data width, that means how many bits the full adder can have, right? And I said here 8 equal 8. Then you close the parentheses and you open the parentheses for the input outputs. There, carry in, there is just 1 bit carry in, right? While if I have 8 bits full adder, that means, each operand will be 8 bits. Do you agree? So in that case, port A, so that's why look, I name it what FA underscore n bits because the name here, right? Underscore port underscore A, and this is width is what? No, whatever this value -1 to 0, which is basically 8 bit. So if I have 8 bits, it's gonna be 7 to 0, correct? 7, 6, 5, 4, 3, 2, 1, 0, 8. If I would like to have a 4-bit, 3, 2, 1, 0, 4-bit. So that's why I said data width -1, and then column 0. Then port B, same thing. Then the sum is taking the same numbers of the A and B, so gonna be data width -1 to 0. And the carry out is just 1 single bit. So far, so good.
Yes.
Okay. Now, since, if you look carefully, if I have a chain of full adder, this carry in, this carry out will be a carry in. The other one will be carry out, will be carry in. Carry out will be carry in, right? So it's connected like in a chain, right? So you can actually make a very nice wire that will be taking number of full adders in the consideration, right? Because you're gonna use them all the time, one to pass to the other, right? Then I made a trick, which is basically instantiating the full adder for the first unit by itself. And I said, that guy will have the carry in here, and the operands are gonna be the first bit of the A with the first bit of the B, and that will generate the first bit of the sum. And the carry out for me is gonna be what? The bit number 0 in the bridge. Okay? Now, anything else coming after that is identical, right? The uniqueness thing, it was that carry in coming in, right? And I can even trick you and I make it even better than that. But can you see it? There, now we're gonna use the thing that I mentioned to you guys, which is called gen var. So if I want to make a for loop, do you remember in C, right? You make a integer I equals 0, whatever, right? So you have to define the index, right? So that gen var I basically define the index, right? Then I said index, start from 1, less than data width, and increment yourself 1 at a time. Sounds good so far? Then you have to, of course, use generate in the beginning, because generate will help you to replicate the blocks instead of you replicate it by your hand. After that, I will instantiate the block that I would like to repeat it many times. And I put here, if I put here I minus 1, I put here I, and I put here I. Let's make a nice simulation. If I is equal 1, right? Here, bridge will be what? Bridge of 0, right? Here we're gonna be what? Port A of what? 1, right? Here we're gonna be what? Port B of what? 1. Here we're gonna what? Sum of 1. Here we're gonna be what? Huh? Bridge of what? 1. Do you guys agree? So literally, that carry in, that carry out became carry in here, right? And that 1 will be with us. Let's say I is equal to. When I equal to, comma, I equal to. In that case, bridge will be what? 1. Here, I equal to. They're gonna be port A2. Here, they're gonna be what? Port B2. When is I equal to, right? Then you know here, I equal to, they're gonna be what? Sum equal to. Then here gonna be what? I equal to, so gonna be what? Bridge of what? 2. Then you move forward. So does it make sense to anybody?
Makes sense.
Irving?
Yeah, it makes sense.
Clispert?
Yes.
Okay. So then we need the carry out, right? So the carry out, there is something called data flow machine. So data flow machine, I just use assign because I assign value to wire. That's it. Which is basically saying that be sure the last bridge is basically carry out. That's it. So now officially, I did what? I used for generate in full adder. Let me show you something. Since I put here width 8, right? Look what happened. It generated the first block and 7 after that, right? Let's change this to be what? A value like 32, right? Make it 32. Let's wait, we'll see what will happen. See what happened? It became here 32, the first block, and 31 got generated. Let's see here 1024 bit. What happened? 1024. The first one is here, and you know 1023 block have been what? Created. So in that case, I built something what? Very what? Flexible. Do you guys agree?
Yes.
That's why it's embeds. Sounds good. Now, testing it is not really hard. Testing it also is a piece of cake. Let's make this 8 or something because that takes some of my memory. Anyway, now we're gonna select this as a top design and we stop here. And then we're gonna go into the embeds and we're gonna consider it also a top design for the TP. If you click on the TP, you will find out something I made here, which is a little bit different than normal test bench, right? So I kept the input-output port of the test bench empty. Do you guys agree? While I created a parameter for the level of the test bench, and I call it data width underscore TP, test bench. Then I created, do you remember the signals that I created last time, right? The input are registers, and I created them also with a TP. and the output is wires, so I put them as wires, right? Then I instantiated the fn bits, but before you call a name, I parameterized it, and I tied with the parameter of what? Huh? I tied with the parameter of what? The test bench. What?
Never mind.
Then I connect the input and output and start putting some initial values and so on. Does it make any sense? So far, so good? Hello?
Yeah.
If there is something is not clear, stop me and say it's not clear. Okay, now, if you want to run the simulation, we can run it and see how it's gonna look like. I made this 4-bit, right? And I put here 15 and 20. So 15 and 20, how much it will be? 35, right? So we run simulation behavior and see what. Oh, it's finished, right? So we're gonna go here in waveform. And since I change it, so I'm gonna go here and take a copy like this and move it up. And then I say save. Then I will go into the beginning of the time. Then I will ask for running. And of course it's closing because after 100 nanosecond will be closing. Then, you know, if we go like that, it will show us. So we said here, the value is gonna be radix. And we want it to be what? Unsigned decimal. So we said 15 plus 4, right? Somebody will tell me, hey, but you know, Professor Ali, you said 20, right? But the question for you guys, is it 4-bit can be 20? 4-bit will hold how much?
16 or 15.
So if you go here in 20, for instance, what is 20 in the binary? So 15 is 1, 2, 3, 4, right? Five. So 1, 2, 3, 4, 5, right? So this 15. 16 is like this, right? 16 is like this. 1, 2, 3, 4, right? 17 is like this. 18 is like this. 19 is like this. 20 is like this. So this is 20, right? Look, it's a 5-bit, but those guys represented in how many bits? Huh? 4 bits. So that means whose will be taken? Those 4. And those 4 representing what? 4. That's why this guy is holding 4. That makes sense? So truncated on behalf of you. Even though that I wrote it here, what? 20 as a decimal. Does make any sense?
So if you were to increase the data width, then you would get.
Then it will be perfectly fine.
Okay.
So let's do it. Let's do it. That's a very good point. You know, let's make this 5-bit, right? Then we say rerun simulation. Sorry about it because, you know, I'm using Microsoft Surface Pro 3. I don't think this is really meant for heavy computation. You know? Super. Now we're gonna go and see what happened. What is the value there? Huh?
20.
It's 20 now.
Exactly. So 15 plus 20. Where's the output? The output, it's basically this. So we're gonna go here and say radix and sign decimal. It became 3. Why 3?
The bandwidth isn't enough for the full value.
It needs 6 bits to represent 35.
Yes, it can be. That's true. So in that case, what we can do, we can go back into the 5 and we make it 4 again. And we can put this value within what? The range. Let's make it 12. And we remove this so it will not be confusing anybody, right? So if we run here, no, still gonna be higher, right? So let's make it 12 plus 3, right? So it should be 15 here, right? Let's see. This card. What is now the value? So did you see? Testing is not just writing code. You have also to analyze what's going on around you, right? To figure out what is the right solution. So for instance, if you like to play more with that, you can just go ahead and say that, this is not enough. We can actually go ahead and say, for instance, after maybe 40 nanoseconds, do something else, right? So for instance, we can just go here and say that, elevate the awareness of the, what's called the carry in and make it 1. Make this, for instance, 9, right? Or make it 7. And let's see what will happen. What happened now? 3 plus 7 is what? 10. And there is 1 in the carry in. That means gonna be what? 11. 3 plus 12 is 15. And 0 in the carry in is gonna be 15. It's perfectly fine. And have you noticed the data width here came, as a parameters, you can fill with any values you want. So now, does it make any sense to everybody? Is it clear to everybody?
Yeah.
Perfect. So the last part that I actually promised you guys about, which is looking into the how can you communicate with the board, right? Then we'll be done for today. So my example that I ran to my team, it was like, sit as a top for the FA, right? And make also the test bench, the right test bench, so we will not interfere with other information, right? Then, if you remember, there is something called at source, right? For us, we created there the constraints for the board. My board is old, is Nexus 4, but you can get the Nexus A7 XDC file. But in general, here is the XDC file. It has all information about the ports you're gonna communicate with. And luckily, in the full adder, I just use 3 switches and 2 LEDs, right? So here is the 3 switches, 1, and I skipped 1, and then I turned it on 1, I skipped 1, and I turned it on the other one. And I filled the name of the port based on the name I have on the FA. So FA has the official carry in, it's called FACN. So that's why there is called what? FA_CN. And there, the FA_port is also there as another switch. and also an FA port B, that's also another switch. And then the devices on the ports, the board that will be acting as a output representer will be LED. So they support some out. I put here the LED list, the first LED out of the 16s I have, and the last LED out of 16 I have, it has the name of the carry out. Then everything is perfectly fine. There is no clock I'm using because it's actually combinational circuit experiment. You will just go ahead and generate bit stream, and there you can load it on the board. And I believe you guys already have it in the lecture, right? Lesbert.
Yes, we do.
Okay. And you can also watch my lecture for refining if there is something is missing. Now, we know what is exactly the task. We know how can we get the task done. Is it clear? Hello?
Yeah, I believe so.
Okay, no, I said, what is the purpose of naming the block? Oh, naming the block is basically allowing the regular expression to add numerical into it. So you will have a different instantiation. So the instantiation trick is to have a name for the thing. So it's taking like a copy from the root to make it like a tree leaf. Doing the same job. Like, you know that trick in software is called, parents and children, right? Same thing. It's a software thing. Okay. Any questions so far? Any concern?
In our simulation, what does it mean when you have an X for the value?
What do you mean?
So when we do our simulation for my FAN bits port sum, I get an X for the value.
If you get X for the value, it means that, there is race condition. That means there is two wires connected to the same wire, an output wire.
Okay, thank you.
Then you have to be careful. There is another color called Z, which is blue. That means, this wire you are trying to present, the output of it is connected to nothing. Okay. They call it high impedance. Okay?
Got it.
The exit will, for you in the waveform will look red, I believe. Okay, look. Okay, guys. Any question before we finish today? Now, delivering. When are you gonna deliver for me this experiment? Wednesday, next Wednesday. You have until midnight. Sounds good?
Sounds good.
You're gonna load everything in where? Your GitHub repo under a folder you create is called what? Lab 1. And you will put the date of the due. And then, you will open, if I open this, I click on it, I will have two subfolders. One is called coding, one is called what? Document, and so on. Okay, Luke? Okay. What it should be written in the report? That's something also you guys haven't asked about, right?
Right.
So the report should have what? Your contribution in the group. Like, let's say that your group is 2 people, right? So that means, I want both of you to work equally on it. There is no way, one made the code and then one wrote the report. That doesn't make sense to me. This is the coding in the what course. Then, followed by what? The theory. Did you see the theory? Here is the decoder. Then, replicating it, how much it will be. Okay, how are we going to make it what? Generic. Then you will create something here about, resources. Have you guys seen the resources before?
No.
Okay, so let's run the example of resources here. So I will say generate bit stream, okay? and I'm gonna use 8 of my threads on the PC to finish the task. So if you look carefully here on the design runs, right? There is total power, there is failed routes, there is lookup tables, there is flip-flops, there is BRAMs, there is URAM, there is DSP. Those are the resources on the chip, okay? Most likely this specific thing is gonna be lookup tables because, you know, flip-flop is basically for sequential and our task is what? Combinational. Do you agree? Lookup table used for combinational circuit. So you give me the number here. The number will be written here, okay? And also the total power that is consumed. Do we just need a report? What do you mean? Huh? Do you remember? You're gonna have the report, the presentation, slides, like how did you do it? You're gonna, when you turn in next week, right? You're gonna have 2 folders, right? Codes and documents. On the document, you're gonna turn presentation, like 2-3 slides about how did you work? What mistakes have you faced? How did you overcome? Stuff like that. Then, you know, a report, which is 1-2 pages maximum, which is showing me also who's contributing, who's not contributing, and a demo, something on the board running. That makes sense?
So we need to have a demo for next week?
Huh?
For next week, we need to have a demo?
Yes, yes, yes. You want a sample for what? For the report, right?
For the report and presentation, just to see how you want it.
Presentation, I will leave it for you. But, you know, report, I can get you a report now.
So you just want like just a simple PowerPoint, right?
Yeah, pretty simple.
Okay. Thank you.
Let me find some report for you and give it to you now.
Thank you.
Professor, when it comes to the resources for the report, you just want us to say this is the total power consumed and stuff of that sort?
Yeah, total power, number of lookup table used, number of flip-flops, number of VRAMs, stuff like that.
Okay.
1 second, let me grab you the most recent report I used. Can you see the Vivado or not?
Yeah.
See, lookup table is what? 1. And in front of what? Synthesis. It's still running. Right? Okay, I found a report. Let me download it and I will post it on the Slack, okay? Here is the report from my team who joined NASA. Here. Everybody can see the Slack?
Yes.
Yeah. Can you see my Slack now, right? Here, can you see it?
Yeah.
Here's the report. You just need to download the PDF. It will be fine. Stop sharing. Wait. Let me open it in a very nice way so we can see. Okay, here, share again. Can you see it?
Yeah, we see it.
Look, the fancy stuff they're making. Top architecture. Then you know how it works. Then you know whatever state machine, code details, corner cases, waveform, information, test bench, right? They were working with some UARTs. It's very advanced than you guys. But anyway, they put the circuits. Then you know they put you the lookup tables and information. Can you see it? Power usage. Utilizing the system. I'm gonna show you that now. Okay, but at least you understand how the report look like, right?
As for the demo, like the video, are we like uploading like the video file or
Yeah.
like a
Yeah,
link
I mean,
for
whatever.
like a
You can
YouTube
make
or
a
something?
YouTube and you put the link. That's fine.
Okay. What's faster, so easier?
I think
for us?
YouTube is better, right?
YouTube? Okay.
I think so.
Thank you.
You are most welcome. But at least now you already have a report, right? I put it on the Slack, right?
Yeah.
Just wait a little bit for this to be done, okay? See now is what? You see that? It's 1-1, right? So that means the final is 1-1. After the generated stream is happening, you will see number here is called total power, okay? And I will show you how can you generate it. While we are waiting for this to be done, everybody can see my my cursor, right? I stopped here on what? In open synthesized design. Can you see it?
Yeah.
And there you can just say report power. See, 2.816, which is okay because we are using IO. We are using LEDs and switches. If I use less IO, the power significantly will go down because that's called bare metal. Yeah, my PhD was in power optimization. So that's why I'm really interested in power, you know. So. Can you see what I did, right? You should just say okay for the power, that's fine. Running power estimation because it's an estimator. Everybody can see that? Let's say, yeah, we can run hardware now. I will do it later. But anyway, look. What is this? That's the power. It's telling you the power on the chip we are using is 2.81 watts, and 96% of it is dynamically used, while 4% is static on the device, and 98% of the total amount of power is coming from the IO that as I told you, right? Because we're using IO. So that's 2.6 whatever. Because we use just one lookup table, it's the logic and signal, it's almost like 0.036 watts power consumed. You see what I did? If you like to see the circuits got built inside the chip, you push schematic. And did you see there? Can you see it? Here is the port A, port B, port C. Those are the buffer to pushing it in. That's why the power coming out of those buffers. Then there is two level of the lookup table has 3 input and 1 output. That's why they call it 3. Going into 2 buffers, OBF output, and connected to output of here. But somebody would tell me, but you know, hey, you told us design run is 1, even though that in the schematic there is 2 lookup tables, right? But the whole idea that, you know, those guys can be resorted in 1 lookup table, 6 inputs and 1 output, or even 2 outputs. Any questions? Hello?
No questions.
Okay, if there is no more questions, I would like to thank you guys for the time for attending this lab. This is a very long lab. In the future, will not be like that. In the future, will be like, you know, talking about the theoretical stuff, what is exactly needed from you, then you can just go ahead and continue work. And if you have questions, just like ask me. That makes sense. But today, because, you know, like introductory. Okay, Duke?
Yep, thank you.
Thank you, guys.
Thank
I'm
you.
looking forward to meet you in person soon, okay? Then situation slightly will be changed.
Looking forward to it.
Okay, God bless you guys. See you then. Bye-bye.
Bye.
A copy of all of this stuff will be loaded on the under the lab, okay?
All right, thank you.
Thank you, bye-bye.
Thank you, Professor.
Bye.